All right, we started section 10.4 last time, and we hit primarily on measures of central tendency, which is how data sort of bunches up, either in averaging, doing what we would consider a mean, or how data looks with modes. So there's a lot of values that are very, very similar. Sometimes we have more than one value for a mode, and then median, which is an actual 50th percentile value, where half of the data is below and half the data is above. And we left off on taking a look at one graph, basically, that showed the relationship between those measures of central tendency, in particular the median, and some variation by looking at the box and whisker plots. And so what we're going to do today is we're going to move on a little bit more in that area by taking a look at two different kinds of deviation. So the first one is called mean absolute deviation. This makes use of the absolute value to find the difference in each data point from the mean. It's found by taking all absolute value differences and then averaging them together. So everything that we're looking at in the next couple pieces anyway are measuring how far away are you from the mean. That's really what they're doing, is how spread out are the values that we're looking at. So the first thing to take a look at when we're doing a problem is to actually find, I didn't say it right, hang on. Yeah, is to I'm going to show you all of them, then I'm going to do an example. That's what it is. Let me just come over here. So when we're looking at both of the types of variations, the deviations that we're looking at, we're always going to be starting by finding the mean. That's the big deal. Okay, so we have to figure out where the center value is, and then we're going to figure out how far apart things are spread. The other type of deviation is called a standard deviation, and one of the most time-intensive part is by finding variation, or the variance first. So I already mentioned finding the mean, so that's step one, to find the mean. The second step is to subtract the mean from each number. The third step is to square the differences of those mean and individual values from step two. That should say step two. That's awesome. And then on number 4, it should say find the sum of the squares in step 3. Very nice. Got some corrections to make. And then the last one is to divide by the number of values. This finds a quantity called variance. And if you take the square root of that, that's standard deviation. So standard deviation is simply the square root of what we just described doing. And I find the easiest way to do all of this is within a table where I can keep all of my data sort of organized together. So we're going to find the mean absolute deviation and then the standard deviation for this same set of data that we've actually used before. So you'll recognize maybe these numbers from last Friday, 18, 22, 22, 17, 30, 18, and 20, and 18 and 12. And what we would like to do first is to find the mean. And we did that. So flip back, if you would, in your notes to where that section was. And what did we find the mean to be for this data set? 19.9 is correct. So this is the step one for no matter whether we're finding the mean absolute deviation or the standard deviation. We got to know what the mean is. So I'm going to show you how mean absolute deviation, MAD, if you will, looks. So we have each of our data values, and I do mean each one of them. Even if they're duplicated, we're going to write them down. If you want to write them in order, you can. I'm just going to keep them in the order they are because it doesn't make any difference. And I don't want you to feel like for some reason that it does. Okay, so these are all my data values. And the first thing I'm going to do, again, in either case, is to find how far away they are from the mean. The difference is that when we're looking at mean absolute deviation, it actually tells you that we're making use of the absolute value to do this. So I don't really care if they're bigger than the mean or smaller than the mean. I just want to know how far away they are. It's just a distance. So for what we're really working at here, I'm trying to find if these are my x values, let's say, and my mean is x bar, I want to find the absolute value of x minus x bar. I just want to find out how far away I am. And if you think about distance and how far away you are, it's actually easier to calculate probably than to take your calculator and to do the subtraction. But that's just, me. So for instance, if I'm doing 19.9 and 18, how far away is 18 from 19.9? It's 1.9. How far away is 22? And if you want to grab your calculators, you can. I'm just sort of throwing it out there as an option. How far away? 2.1. Yeah, it's the 22 this time is bigger than the 19.9. And I've got 2 of those, so I've got another 2.1. How about 17? Yep, that's 2.9. 30? 10.1. I have another 18. I already had that, so that's 1.9. And I have 12. 7.9. Okay, so this is how far away each of them are, excluding sign. I don't care about the sign. How far away are they? And then what we're going to do, my picture's just a little bit too big, so let me shrink it a tiny bit, is we're going to add them all together. Okay? So you're going to do a sum here at the bottom. So what do you get if you add them all together? What'd you have?
28.9.
Good, that's what I have too. 28.9. Does everyone else have that too? Yeah, good. And we're averaging, so we're going to take that 28.9. So the mean absolute deviation is to take the 28.9 and divide by how many data values I have. And how many data values do I have? It's not a scary question. How many? I had 7, yes. So divide by 7, and what do you get? .1. So this is saying that on average, our values are 4.1 away from our mean. Down 4.1 a little bit lower, up 4.1 a little higher. That's the average distance that we are away. Make sense? But that's only one way to find average distance that you are away. It's the mean absolute deviation. We're going to do the same thing that we just did, but we're going to do standard deviation. But the process at the beginning starts out the same. So we're going to have a mean over here, which we said was 19.9. And we're going to make a column for the scores and then for the absolute value. So the first 2 columns are going to be the same columns I just created, no different at all. So this is x, this is x minus x bar. If you look in your book, they may not do it as an absolute value, but I'll show you why in a minute I am. Okay, so I promise I'll show you that. But let me do 18, 22, 22, 17, 30, 18, and 12. I had 1.9, 2.1, 2.1, 2.9, 10.1, 0.9, 7.9. Okay, so just repeated so far, yeah? I'm not adding them together, though. What I'm going to do for my next step is that I'm going to actually square them, and that's why I'm doing absolute values, is because what happens when we square positive numbers? Gives you positive numbers. What happens when you square negative numbers? Does it give you positives or negatives? It gives you positive numbers. So does the sign matter? Nope. So we might as well just ignore the sign to begin with, because I'm going to square them, and it's going to remove it anyway. So what I'm going to do here then is I'm going to take that x minus x bar, and I'm going to square it. Put the absolute values, don't put the absolute values. It makes no difference. They'll be the same. So what is 1.9 squared? 3.61. How about 2.1 squared? 4 point something. Okay, and I have 2 of those. How about 2.9 squared? All right. 10.1 squared. Good. 1.9 I already had, so that's 3.61 again. And the last one is 7.9 squared. Awesome. Okay, so I've got the squaring column. And then I'm going to sum, okay? So this is the column I'm going to sum on this one. What is the sum of the squared column? Awesome. And then, what do you think I'm going to do with the 188.87? In a minute I am, but there's something I do before I square root. Go back over to that list. The one, this one right here. Divide by the number of values. Because what I'm actually finding right now at the moment is variance. Okay, look back at the directions on this one. It says to find the variance. So I'm going to find my variance. And that would be the 188.87 divided by 7, which gives me what? Okay, 26.98, or 27 if you were using just one decimal. And then part C is to find the standard deviation, which means to take the variance. So the standard, oops, I'll write it this way. Standard deviation is either done with S or with sigma, which looks kind of like a script R. Either of those are the notation, but we'll use S because it probably will remind you what it stands for because of the letter. So the standard deviation is the square root of variance, which was 26.98. And what is the square root of 26.98? Okay, and we'll do one decimals for our final answers, so 5.2. Over here, if you wanted to leave this as a one decimal, it would have actually said 27.0, if you wish. Okay, so we have 5.2. It's a little bit bigger of a range, right? A little bit bigger of a spread than the mean absolute deviation gave me. So you might be thinking, okay, but what does standard deviation do then? I mean, mean absolute deviation sort of makes sense to us. We're taking an average of how far things are away. But what does the standard deviation do? Well, standard deviation is used in particular when we're talking about data sets that are normally distributed. And not all data is normally distributed. However, larger data sets tend to be more likely normally distributed. And when they are, they follow what's called the empirical rule. So start with normal distribution. And normal distribution is a smooth bell-shaped curve that depicts frequency values distributed symmetrically around the mean. So it looks like this. And right in the middle here is the mean. I'll write it in as x bar. Okay, so there's symmetry around the mean when things are normally distributed. A lot of things that are done in factories would be normally distributed. So if you imagine when you go and you buy that box of cereal that says that it's 16 ounces on the bottom of it, are you sure it's 16 ounces? Or maybe it happens to have 16.2 or 15.5, right? It's supposed to be really, really close. But obviously we all recognize that there could be a little bit of error that we're all kind of like, it's all right. I mean, it's close enough to call it 16 ounces, right? That's a normally distributed kind of quantity. Now, you've probably heard the phrase before, grading on a curve. Have you heard that before? Have you said it before? Are you going to curve the grades? You don't mean what is really meant by curving grades. When people grade on a curve, what it means is if I were to take all your grades, this works terribly with 12 students, but just pretend for a moment. If I were to take all of your grades and I were to get an average, then that average would split the class into halves and halves. And somehow that middle part in that average would be the C range. And if you go out a little bit further, you'd get the B's and the D's. And if you go out a little bit further, you'd get a very, very tiny little tail end of this thing that would be the A's and the F's. That's really what grading on a curve means. If you're dealing with a class at OU that maybe has 500 students in them, and yes, that's something that happens there. My husband had a class like that there. It's probably a pretty reasonable estimation. But in a class of 12, it's probably not, right? So what happens when you do have a normal distribution is that the empirical rule applies. So the empirical rule tells us that within one standard deviation of the mean, 68% of the data would lie in that range. So that's the same standard deviation that we just found over here, 5.2, right? If this data were really evenly distributed, or not evenly, but normally distributed, if you went 5.2 in each direction, you'd have 68% of the data that lies in between those values. Okay? So on my curve that I'm imagining here, if you go out here, this is taking that x, that mean plus the standard deviation, and that mean minus the standard deviation. And 68% of the area under the curve, right, is in there, 68%. If you go out 2 standard deviations, right, so with this data set, if you went out 10.4 in each direction, right, 10.4 to the left, 10.4 to the right, 95% of your data would fall in between those values. So I'll mark it over here and here. So I'm going to write it up here just because I'm out of space. This is the mean plus 2 standard deviations, and this is the mean minus 2 standard deviations. And then if you went out 3 standard deviations, you can hardly see it on mine, you'd have 99.8% of the data. Okay, so again, please remember the empirical rule only applies if you're dealing with normal distributions. So in order to actually make use of the empirical rule, let's say that you were asked to create a problem. I may or may not have done that on a previous test. I have before, right? And you don't tell me it's normally distributed. If you don't tell me it's normally distributed, you can't start talking about empirical rule because it doesn't apply. It only applies to normally distributed data. So we're going to do some examples of this. You start out seeing the very phrase that I'm talking about, right? Assume a normal distribution. It says the average phone call in a certain town lasts 8 minutes with a standard deviation of 2 minutes. What percent of the phone calls lasted between 6 and 8 minutes? So please write yourself a note right on your paper right now that says, draw the curve. All right, I'm going to expect to see a picture with every single one of these. Perhaps you can think through the visuals well enough that you could do it without a picture and get it right. Most of us probably can't. I'm a very visual person, and it would be very difficult for me to get this right without a picture to support what I'm doing. So we're going to draw a bell curve. I'm not judging your artistic ability. Mine stinks, so I'm definitely not going to judge yours. But it should have, a bellish shape. And it should be marked right here what the mean is. So what did it say the mean length of the phone call was? 8 minutes. And you can leave the minutes part off if you prefer, but I'd need to have the number 8 written down. What did it say the standard deviation is? 2. So as I move out in each direction, if I'm moving to the right, I'm adding 2. So this would be 10, 12, 14. And if I'm moving to the left, I'm subtracting 2. 6, 4, 2. So far, so good. Okay, what we're going to do next is we're going to shade the part of the graph that is what they're describing. So this says between 6 and 8 minutes. So that's here. Shade with your pencil, shade with a colored pencil. I don't care what you do, but it needs to be marked. Shade it in, what part of the information that we're actually being asked about. So this is part A because it says between 6 and 8 minutes. Just for fun, I'm going to unshade it for a second because I'm going to use the same image over here for part B and part C. So I'm just going to paste mine over here. If you want to change colors between yours, that'll work too. Okay, now I'm going to go back over and shade again. Okay, 6 to 8 minutes. So, what percent of the data is in that blue region? That's a really good starting spot, Kira, but it's not 68.
34.
So why is it 34, Hannah?
Because it's like cut in half, like the 8 and the 10. Between 6 and 10 would be 68.
Yeah. So all of that would be 68, right? So you're totally in the right place to start, Kira. 68 is where we want to begin, but we need to recognize, like Hannah said, that it is actually only half of that because I'm from the mean over to the left and not to the right. And so if I take my 68 divided by 2, I would have 34% of my data. Okay, does that make sense to everyone? Okay, so we're going to be doing some reasoning abilities like that as we continue to work. The next one says that I'm supposed to have a phone call between, or that lasts less than 4 minutes. So less than 4 would be over here, and it needs to go past the 2, okay? Like, goes all the way down. I mean, technically, I know it can't go beyond 0. It's not a problem, but it just shades to the left. Okay, there's more than one way to do this problem. Tell me what you're thinking. Okay, so 99.8. So where are you getting the 99.8? Like, what's it coming from, Brooke? The third standard deviation. So what you're describing would tell me the amount of data that's right here. That's not what we want, though, right? Okay. So let's try again. What else might we try? Okay, so if I did the 95, I would be finding the data that's right here, which is very helpful, but it's not the answer, right? The answer is not 95 because the part that's shaded is not the part that I just drew in that purple rectangle, correct? Any ideas about how I could use that 95% though to find what I want? Okay, so where are you getting 5%, Summer? Okay, so what's inside here is 95. Everybody's good with that, yeah? So what that tells me is the part that's left over out here has to be 5. Everybody good with that? It's 5% on the outer edges because it's 95% in the middle because of the specific middle we're dealing with here. Okay, so is my answer 5%? No. It's 2.5. So why is my answer 2.5%? Yeah, I only have the smaller edge, or not the smaller edge, but the first edge, the left-hand edge. I don't have both ending pieces, right? I just have half of them. So this is actually going to be the 5% divided by 2 to give me 2.5% of my data that is below 4 minutes. Okay, part C. Sorry, I'm going to have to flip the page on that, and for you too. Once more than 12. How does it last more than 12? Yeah, it is. It's just the top half edge of what I just found out from the bottom half, not half, but corner, right? This is the top corner. So it's the same thing, still 2.5% of what I had before. Okay, you ready to try another one? We're going to shift the context a little bit. The mean IQ scores for 1,500 students is normally distributed. There's that phrase. We got to have that in there to start drawing bell curves, right? Normally distributed with a mean of 100 and a standard deviation of 15. And then it wants to know how many students have an IQ between 85 and 115. So I'm going to draw a bell curve. What is my mean? 100. What is my standard deviation? It's 15. So I started 100, and I'll just fill in everything on the upper half by adding 15 each time. So this is 115, 130, and 145. And then I'll subtract 15 every time. So this is 85, 70, and 55. Okay, is the picture set up okay? I'm going to use this same setup for parts B and C in a moment, so I'm going to copy it and put it over there. Okay, and we're going to start this process just like we did in the last problem, shading in the description that it gives me. This says between 85 and 115. Okay, so what percent of the data lie between 85 and 115 on the IQ scores? I promise it's not a trick question. It's 68%. Yeah, it's the empirical rule, 68%. The part that we haven't done yet is actually answer the question that's being asked, because what does the question actually ask? Yeah, how many students? Now, we still need the 68% to find that, though, right? Everybody recognize that? We're just not finished at answering 68%. So I need 68% of the 1,500 students. But we've done that, right? We can do that with a proportion. There's other ways to do it, too. I'm going to set it up as a proportion because that's how we've most recently seen it. 68 over 100, that's my percents. I want to know how many students that is out of 1,500. So if I cross multiply, what is 1,500 times 68? Awesome, and then I can divide by 100, right? So how many students would that give me? 1,020 students. It's a lot of them, right? I mean, roughly 1,000 of the 1,500 is in between those data values. Let's try another one then. We want an IQ over 145. Whew, that's pretty high IQ. It's over here, right? Top little corner. So we still have to start with the same question we started with before, which was, what's the percentage that gives me? So what percent is that going to give me in that top little corner like that? It would be 2.5 if it started at 130. But this time it's starting clear at 145. Nope. These aren't even, right? Like there's not as much data here as there is here. They're not equal. So you can't just divide by 2. What other thoughts do we have? Okay, where'd you get 0.1? Okay. Good, so I'll do a red rectangle again this time. This would be 99.8% of the data, right? From 3 standard deviations on the left to 3 standard deviations on the right. So how much does that leave in the outer areas over here? 0.2%. Not 2%, 0.2%. So in just the top corner, not the 2 corners, I would have half of that at 0.1%. Again, not 1%, 0.1%. Yeah, so we can set up the proportion like we did before. So this is 0.1 out of 100 equals x over 1500, and we can cross multiply. So 100x equals, so what is 15,100? What do I have? I put too many zeros. I was like, that doesn't sound like the right number. 1500. What is 1500 times 0.1? It is. It's 150. And if I divide it by 100, what would that give me? 1.5. 1.5 what? Students. We need to round. Yeah, we're not gonna go dividing. This isn't a magic show, right? We're not chopping people in half. So we definitely need to round, and we'll just use regular rounding rules. So if this had said 1.4, we would say 1. If it says 1.5 and up, we'd say 2. So this is 2 students. So there are an estimated, right, 2 students in the school of 1,500 who have this IQ that's really, really high. All right. One more of this variety. We've got to go between 70 and 145. So here's 70 and here's 145, and we'll shade in between them. Okay, so the first thing I hope that you look at that and recognize is it's not symmetric, right? It's not just one of the numbers off the empirical rule chart. It's not 68, 95, or 99.8. It's somehow going to combine a couple of those things. So what are your thoughts on how you might figure out what percent first that is?
Wouldn't you do the 68, and then you would add the,
So 68, Bethann, gives me this part of it. Is that the one you wanted?
no,
Okay.
the 95.
Okay, so one way to do it is, as Beth said, we could start with this being 95%, and then it's going to tack on a little bit more. I think there might be an easier way to do it, because finding that extra little bit that we're tacking on is going to be kind of messy at this point, messier than my other option anyway. What if I found this part and this part separately? The part that's in red, how much would that be? It would be not 34. 34 would only give me from 100 back to 85, but you're thinking along the right lines. How much is there? Okay, Brooke, I heard yours first. So how did you get 47, whatever?
Well, that's the negative side of the 2s, or the mean minus the 2s, so that would be the 95 divided by 2.
Right, okay, so it's the 95 percentile, like that's the empirical rule portion of this, and it's half of it, so it'd be divided by 2, so this would be 47.5, is that right? Everybody good with that? Okay, cool. All right, let's do the same thing with the purple one then. How would I find out what amount the purple one is? Yeah, it's the 99.8 piece, right? And then divided by 2. So what do I get for that one? I didn't write this part down. What is that? 49.9%. So how could I find the total percentage? Thank you, Kira. Yes, I would add them. 47.5 plus 49.9. How much percent is that? That's really good English there. 97.4%. Okay? Once I get to the percentage, the process works the same way it did on the previous parts. I need to figure out how much that is out of 1,500 students. So I have 97.4 out of 100 equals x out of 1,500. So this is 100x. What is 97.4 times 1,500? 146,100. Okay. And then dividing by 100. So how much is that? 1,461 what? Students. Yes, indeed. 1,461 students. Okay, any questions on that? There's one more tiny bit in this section. Let's take a look at it. This is percentiles. Percentiles shows a person's score relative to other scores. For example, a score in the 90th percentile means that approximately 90% of all other scores are lower than this score. Most standardized tests that children take are in percentiles. So when a child gets back a report when they take their state tests and it says they're in the 50th percentile, that doesn't mean they got half of the problems wrong. It actually means that half the kids who took the test did better than them and half did worse than they did. And it's very frustrating because that means that those children who maybe did really well, if they all do really well, look like they didn't really do very well. Do you see what I'm saying? It can be very difficult. And then it's the same thing when they start ranking, schools and things like that, or when you start looking at, like cost of living, like we're the so-and-so percentage of the, like we're out of 50 states, we're somewhere in the middle. Well, somebody's got to be above, somebody's got to be below. And if we start shifting people around, I mean, there's always going to be the people that are in the lower percentiles. The same is true for percentiles in other areas. Test scores are not the only area. One of the places, many of you will probably encounter this at some point, I suspect Danielle already has, that when you take your child to the doctor, Danielle, they like to put them on a growth chart, right? And they will tell you where their height, their weight, and when they're really little, their head circumference is in percentage to other children their age. And they use it for really good stuff. Like my son, when he came home from Ethiopia, his head was too large. It just was. He had a mild case of hydrocephalus. It's never affected his ability to learn. He has no problems with it. But they kept a really close eye on it for a really long time to make sure that there wasn't anything to be alarmed about. They like to look at percentiles, differences between the height and the weight. If there's a big gap between percentiles of height and weight, that's alarming to physicians as well. So like my littlest one that's in my house right now, she's in the 15th percentile in height, and I think that's right. And she's in weight, 15th percentile in weight, and she's in the 60th percentile in height. That's concerning to them. Those percentiles should be closer together. So they look at percentiles for lots of things, but they're used quite frequently to kind of give you a sense of comparison, right? It's a comparison of the data. So we're going to take a look at an example of Junior. Junior was ranked 50th in his graduating class of 325 students. Liz was in the 75th percentile of the same graduating class. Which student had the higher GPA when they graduated? So we're trying to compare things that aren't really in the same type of comparison, right? I mean, one of them's talking about the 50th person and the other one's talking about the 75th percentile. Something's got to give. We got to change something in order to actually be able to make this comparison. So you have a choice, and the choice is yours. What would you like to change and how to actually be able to decide who has the higher GPA? You want to work with Liz. Okay, so it says Liz is in the 75th percentile. So if I'm working with Liz, I've got to figure out where she is in class rank. Okay, so how would I do that? How would I figure out where Liz is in her class rank? Is it 325? Yeah. Okay. Now, one word of caution. This is a great place to start. What will I actually find at the end, though? will I find how far she is from the bottom of the class or how far she is from the top of the class? Right, like 50th, the fact that he's ranked 50th means that there are 49 people above him, right? There's 49 higher, and there's a lot of people lower. Will this calculation for Liz find how many people are higher than Liz or how many people are lower than Liz? What is it? It'll find how many people are lower than Liz, which is totally fine. You just need to be aware of the answer coming out of it, of what it's actually giving you. So since I've already written down the calculation, let's do it. I have 100x. What is 75 times 32.5? I absolutely don't have this written down at all, so. Oh, I'm sorry. It's because my pen did not keep smooth. 325. Thank you very much. 75 times 325. 24,375. And if I divide by 100, I'm going to get 243.75. And like I told you before, we'll round, so this would be 244, right? 244 what? Yeah, it's people below Liz. So I know how many people are below Liz, and I know how many people are above Junior. So I'm getting closer. What would I actually need to do to find out the opposite information for Liz? How many people are above Liz? Yeah. So if I took my 325 minus the 244, what am I going to get? 81. Right? So Liz is ranked 81st. Right? That's what we just found out. Liz is ranked 81st. So which student had the higher GPA when they graduated? Junior did. Because his class rank is higher. Okay, so think through with me for a moment. We're going to just chat about this one. This won't be due next time. We'll do the group work and assign this for later. But how else could we have tackled the problem? There's at least two other things that we could have done along the way that would have looked different and still arrived, of course, at the same solution. Let's do the very bare minimum of what we've got right here that we could have changed. Instead of finding 75 over 100 equals x over 325, what could we have done instead? We could have done 25 over 100, and that would have given me Liz's class rank. At least they both would have been very close. I might have gotten 80 instead of 81 or something, depending on rounding, but I'm far enough away from 50, it really still answers the same question, right? I'm in the right ballpark. So that's one way I could have dealt with it. The other way that I could have dealt with it is that I could have changed Junior's information instead of changing Liz's information. So if I wanted to change Junior's information, what would I have done? Say it louder. Yes. Or I could have done the 275, which would be 325 minus the 50, to compare again from the bottom perspective compared to the top, because one of them is measuring from the top down, the other one's measuring from the bottom up. But yeah, I could have worked on changing Junior's into his percentile ranking instead of his class ranking to make that comparison. Okay? Just be really careful when you're making the comparisons that you really are looking at the same pieces of information, because it's really easy to get to this point right here and not remember that these are below Liz, and still you're thinking above Liz, and your comparison might not actually lead you to the right conclusion because you're not quite making the right comparison. Okay? Any questions on that one? Okay, so here's the plan. We will finish this section of material. I mean, we've finished the notes for it, but we'll do the group work for it next time. We will also do, it's a very short lesson in 10.5 next time, and we will do the group work for 10.5 next time in class. What I will do, because I absolutely would hate to give you two homework assignments that are both due on Friday, is that the 10.4 will be due on Friday. Is not going to work. Actually, that works perfectly. They're both due on Monday. I was going to suggest doing one on Friday and one on Monday, but we're off on Friday, so they'll both just be due on Monday when you get back. Awesome. Okay, so that's what we'll do.